Hello everyone and welcome to part 5 of the Streamline tutorial series. Today we are going to be going over particle clearing by spline, so let's get right into it. So first, let's take a look at what our final product will be. So we have a cloud of cube mesh particles here that just float around, and when the spline activates, it carves a tunnel through them, and then as it deactivates, that tunnel collapses. And then it just kind of pulses open and closed, so you can see you can fly through here, and it is quite open. This is just the shadow from over there. And this system has an alternate mode as well, where you can go into the emitter and you can make it a tunnel as well. So instead it gathers a tunnel around the spline that pulses with it. And then when it collapses, then the field regenerates, and then it creates a tunnel once more. This spline will also have the capability to be animated as well at runtime. So if we go and click is animated, we won't see anything noticeable right now. However, when we hop into running this, we will notice we just start out here and the spline will draw itself out and can move. And this way you can ensure your spline is animated however you want at runtime, so you are not constrained to whatever spline you make in the editor. Your particles will follow however you draw it out. In this case, it just reset now back to the original starting bulb, and now it's drawing it back out again. So let's get right into making this Niagara system. So the first thing we will need to do is we'll need to head over to our empty pad right here, and we will need to get our Streamline spline emitter. And we'll want to draw out a spline that we can use for kind of just imagine you're cutting through some volume or cloud with it. So we can draw out a somewhat curved spline, but also still a spline that's pretty straight. When you have a spline loop back on itself in this case, it may not have such a great result in terms of pushing the particles out of the way or into a particular shape. So we will take that shape. We will go to our emitter we just dropped down, and we will go and sample the spline we just drew. Now we have a much longer spline. We can get rid of this spline actor and grab our actual Streamline spline emitter and drag it onto our pad right here. And it is off the ground, which is good. That way you can really get more of a tunnel feeling instead of just it being more of an archway. Just center this on the pad, and we are good to go. So let's go and make our system for this. So we will just have something starting from a fountain system. We don't need any system in particular, but we can call this cloud clearing streamline effects. And we can go ahead and put this onto our Streamline emitter and jump right in. So the first things first, we will need to make sure we are rendering cubes instead of sprites. So we can get rid of our sprite renderer and go over here to a mesh renderer. And right now it's just rendering the nomons, so we can go and search for the cube. There'll be multiple of these cubes. I am just going to go with this one called cube directly over cube 1. Not exactly sure how your directory will look like in that case. I'm on Unreal Engine 5.4, so that may change what directory you're looking at there. But either way, you should definitely have a default cube element you can put in there. And one thing I'm noticing is, just in my preview right here, this is looking really big. So let's go, and in our initialized particle, we will go and we can ignore sprite attributes, but our mesh scale mode, we will want this to be uniform, and we can set this to something like 0.05. Now we're getting these smaller cubes just spraying out here. And if we go into our world here, we can see they're on this end, but they're spraying out. And when you compare them to these cubes here, they are roughly the same size. It will work for the effect just fine. Now, the other thing about these cubes is over here, they have this kind of metallic blue color that turns to red when the spline's near. So we need to make a material for that. So let's go and make a new material. We will call this Cloud Clearing Cube Material. We can open this up. And the first thing we'll want to do is have the color based off of whatever the particle color in your Niagara system is. So we will want to go to a particle color and grab a particle color node. The RGB will just go directly in here, and what we will use alpha for is controlling other things like the specular, roughness, and metallic to give the particle more of a interesting effect to it instead of just this matte flat color here. So what we will be using alpha for is alpha will directly relate to the metallic value of this particle, and it will then inversely relate to the roughness. So we'll need a 1- node, pop this into roughness. This is not meant to be a material tutorial, so I'm just going to be really quick about this. RGB we will multiply with the alpha divided by 100. And this will go into our emission. Obviously in our preview, it's looking pretty shiny. This will change as we give it color and as we provide an input for alpha to manage our metallic, roughness, and emission. So let's apply this material, save it, and close out of it. We won't be needing it anymore. And we can come down to our mesh renderer, and we will enable a material override. And then on our override materials, we will go down here, drop down till we get to here. We can go to Cloud Clearing Cube Material. This will make sure it auto enables the usage for Niagara by doing this. So if we look at it, we can go down into our settings and see it's already used with Niagara mesh particles when we input it just like that. You don't need to explicitly check it otherwise. So now that we have that done, if we go and look in our world, we now have these shiny cubes popping out of this end here and just falling down. That's a start, but in this cloud over here, we notice that they are colliding with the ground and interacting with it. So we will want to add collision for these cubes. So in our particle update, let's add a collision module here. And then one thing we may want to consider is to switch this system into a GPU mode. So that way we can handle more particles, especially when we're considering a large cloud like this. And we will want fixed bounds for this to make this much simpler for the GPU. So usually I turn these up to 1000 so it can still be seen from a good distance and whenever you turn the camera angle. Sometimes if this is too low, you can turn the camera angle or look at it from too far away and it will not appear there. So this ensures that the GPU will still calculate it and you can still see it. This means when we go to collision, we can use the GPU depth buffer, distance fields, or ray tracing. In this case, we're going to use distance fields since they provide a simple collision option here. We aren't worrying about complex collisions. We are basically just colliding this with the bottom of the platform we have set it on. We will set the calculation of the collision to mesh. And for the mesh dimensions, we will provide bounds of the original dimensions of the cube, which are 100, 100, and 100. And then its particle radius will be 1. We'll have a normal restitution, and our friction will also just leave as is. Our rest state is all good, and we will want to kill particles when they get stuck. So now with this enabled, if we go and look, we will see our particles are just bouncing on the ground, but it still doesn't look very real. They bounce into the ground, bounce off, but there's no rotation to them. There's nothing that really gives the feeling that they are actually hitting the ground instead of just some plane and being just told to bounce directly back upwards. So what we can do to sell the illusion that they are indeed colliding with something more is we can, first of all, control the roll on collision. But something else we can do to give them a bit more motion when they're in the air is we can add aerodynamic drag to these particles. And we can get rid of our old drag module here. So we'll also encounter an error here. We can actually just dismiss this. We won't need to worry about it because we are not dealing with sprites in this case. We are using a mesh renderer. And so facing will not make the system have any big issues. So now when we look at this, they spray up into the air and now they kind of float down and start moving more randomly and naturally. And so to see them hit the ground and actually interact with it, we can give them a longer lifetime, but we'll still want it to be random so that they can kind of come and go when they're in the cloud and make the cloud look more fluid. We can give that a lifetime of 5 to 12, something like that. That way they can fall down and they will interact when they hit the ground. Right now they are mostly just sticking to the ground. That can be changed. But now we are getting something that looks a bit more like what we are seeing over here. However, what we have instead of just a point spawning these particles is we have a whole region spawning them. So we will want our shape location to be a box that we can spawn these in. And then from there we will want to add our velocity randomly in a linear manner. So in this case we will have a velocity scale of something like 500 and our velocity will be a random vector from -1 to 1, and then we can get random velocities with a magnitude less than or equal to 500. We can save this, and now they're spawning in, but our box is not big enough, so we will need to make sure our box covers this entire plane right here. So this will require a bit more guess and check. Really, it will depend on what kind of area you want to cover, how big of a box you will need. So we can go here, expand this out so we can see it. And based on where this starts, we can change these values and get larger spawn regions. So here we can see we have this, make it maybe 1,500. Yeah, let's go 1,500. And then we can shift the midpoint over. So we have something that is over our region here, and shift it a bit more that way. Okay, so that looks like it encompasses the length of this area pretty well. Maybe it overshoots it a bit, but that's not the end of the world. And then since this is a square, I can also set this size to 1,500. And now we have particles that are spawning a bit too far over this direction. So I'm going to change this to be a bit larger. And now we have particles spawning. I have particles spawning over this area. They're still spawning in a pretty thin region. First of all, let's turn up the spawn rate a bit higher. Something, since this is a GPU system now, we can handle a lot more particles. So I'm going to set this to something like 4,000. Now we can get this good visualization of what we were working with. I might turn down these sizes a bit more now that I'm seeing just how big this is. Maybe 1,200 on each of these. Now I will just need to shift the midpoint a little bit. So this midpoint to 1. There we go. And so now we have this field of particles that are just spawning and falling down. However, it would be better if they spawned in a larger area upwards. So let's make this something like 750. Now we are getting a high dense cloud similar to what we were seeing over here. To make this a bit more see-through, we can vary the size of these particles. Something from probably 0.01 to 0.1. That way our 0.5 measurement is right in the middle. Now we have this, if you look over here, pretty similar. These cubes in general are smaller, but we can move along and get to something that will get these particles to be smaller in the future soon. For now, let's also make sure we get rid of gravity. We don't want these particles falling, we want them floating, so we can delete this module. And now when they spawn, they fly into existence and they just hang in the air. They do hit the ground. We are noticing some excessive spinning down here. And this can be reduced by increasing our aerodynamic rotational drag. Something maybe more like 2, and then that will exponentially decrease the spinning. We're also getting spinning on the ground. If we look here, it's not uncommon. There are still particles that will spin similarly when they hit the ground. Again, you can mess with your collisions to get whatever you need for your particles. And in fact, to make this more interesting, what we can do is we can actually randomize our drag we have here. So we can do random range floats and make something from like 0.4 to 0.8. And we will get a good spread of particles everywhere. And this can be only at spawn. We don't want that changing constantly. That will result in very strange values. And perhaps let's turn this down to 0.2. And now we get a very dense cloud of these particles spawning. And let's set it similar to these colors over here so we can start getting a feel for what our final system will look like. So let's go to our initialized particle and go to color, and I have copied the hex code for this color from the other system. It is this right here. Feel free to use this color if you want. And we'll notice that the alpha is currently 0. This is, again, so we can manage the other aspects of our particles material instead of just the color. This will come into play more later. But if we look at this cloud is starting to look a bit more like this cloud. The particles here are a bit smaller and more spread out still, but it is a good start. Okay, now to make the mesh size match a bit more closely to what we're seeing, also, now that we're here, it reminds me I need to rename this to particle cloud. But what we need to do is to scale the size of our meshes over time so that they have a more natural way of spawning in. So we will take this curve right here, and we will drag this key, these 3 keys in fact, down to 0. We'll make another key right here around 0.1 on all of these. And we will also make another key on about 0.7 on all of these lines as well. And what we can do is collect all these keys together, and we can drag them up to about 0.9. We want kind of a smooth fall off for our particles, and this can be dragged up all the way to 1. And let's select all of our points on this curve and make them user points so that we get a smoother graph here. And now if we go out and look at our cloud, when we see the particles, they will spawn in at a much slower rate. And if you want to turn down the size of your cubes to match this a bit more, you can go ahead and do that. This is seeming a bit dense still, so I'm going to turn down the size by, I don't know, a factor of 10 again. This might be too small as well. You really need to see, yes, this is far too small. Really just a matter of experimenting with which size works with what you want. In this case, I want my cloud to be still a bit more see-through. I don't want it to be like an impenetrable fog. However, you can make it like that if you would want. So we have our cloud right here. We also have these particles spawning under here. So what we can do is we can lower the height of our box to something more like 250, and then also raise the midpoint of it. If we look at it like this, you will see the problem with these particles that makes them spin is they're spawning underground and then being forced out of it. So if we move this midpoint up a bit, we can hopefully reduce that. Now we still have some frantic spinning, but if we continue to move it up, we can start to reduce that. So now there's a bit less. There's still some as particles hit the ground in weird ways. For the most part, it's stopped, and you will be getting some weird spinning anyways when the spline pushes things out of the way. You'll notice some of these particles go a bit crazy in the bottom there. But let's make it so our spline starts doing that. So to get the spline to push these particles or pull them, what we'll want to do is we will want to add a spline attractive force module. And so what this does is this generates a force based around a particle's distance from the spline. And so what we will want to be doing is we will want to be messing with this attraction coefficient. And so we are good leaving our sampled spline as is. That will get automatically determined as our Streamline emitter spline that we have already built. For the attraction coefficient, we will want to change it over time based on that spline. So what we will want to do is we will want to come here and we will want to lerp between -500, so this way we can get the particles being pushed away from the spline when it's growing. And then we will also want this to be no force at all, so essentially 0. However, if we are making a tunnel with it, we want this to be a different value. So over here, let's go and make a Boolean and call this make tunnel. And so what we can do now is we can make a float from the Boolean. And if we plug in make tunnel here, if this is false, we will just want there to be no force at all. However, if this is true, we will want to do something else that determines whether or not the tunnel is open or collapsed. So in this case, we will be using another Boolean switch here, and we will have a pulling force of 20 on the particles if the tunnel is active, or no force at all if the tunnel is not active. And how we will determine the Boolean here is we will set a Boolean by a float comparison. And what we will check is we will want 0.2 to be our comparison value. And we will have a oscillating sine wave here so that we can have the tunnel open and close over time. And so we want this to give us a period of something like 10, and the scale and bias can be 1. And we will just do this over the emitter age. So that is our B term for the lerp, and then what we need to determine is the alpha. So for the alpha, we will want to, first of all, clamp our results to 0 and 1. So that's all good right there. And our actual float, what we will want to do is we'll want to divide our distance from the spline by the state that the spline is in and how far it is into its pulse, if you will. The first thing we want to do is divide float. And what we are going to do here is we're going to grab a proximity target so we can determine the closest point on that spline from the current point that the particle is at. So what we will do is pull up a distance between positions field here. And we will go and get the particle's position, plug it in right here. And what we will also do is we will get a spline proximity target, but first we'll need to convert the vector output of that to a position. Then we can go spline proximity target. And what we can do is we can use this position again as the proximity target so we can get the difference between this position and its closest position on the spline. We can use that to determine a relative amount of force for how much to push it away from the spline. And then on here, again, we will want a similar switch as we did for above to determine whether or not the spline is currently in its active pulse or not. So we will make a float from a Boolean again. And the reason why we want a Boolean here is because if we are also going to animate this, we will want to have a constant force. This way with a constant force, we can better visualize our animation. You can get rid of this part and just still make it pulse during the animation, but you don't have to do that. I'm going to make it a steady force during the animation so we can see it better. But let's go ahead and make another Boolean and call this is animated. You can plug this in here. If it is animated, I'm going to want a force of 200 on these particles so I can see the spline's tunnel it's making very easily. Otherwise, I will want another sine wave to determine the state of the spline's pulse for the period of 10, scale of 100, as well as a bias of 100 to ensure that the spline stays positive. Otherwise, it's going to dip into the negatives and it's going to push and pull instead of just push. We can save that, and that will now get us our system. So if we look here, you can see it closes in, and then it starts pushing open, and we have our tunnel here. However, it's hard to see, and it just doesn't look very defined this way. So one way to define it is it's already hard to see the spline. So we can go ahead and make a new empty emitter, and this can be our spline ribbon emitter. And we can also set this on the GPU as well with our fixed bounds. And these bounds, we can also bring them up to that 1000 if we want. Okay, so now on our emitter update, we will want to have an emitter state. And in this case, since we are dealing with a ribbon here, what will be a ribbon along the spline to define it much easier in this cloud, we will just simply have one loop that is just fixed, a singular loop duration, and we will have a spawn burst instantaneous right here so we can get all the particles we need to assemble that ribbon. We will have a 100 particle detailed ribbon that will spawn instantaneously. And so we will initialize these particles and give them their shape location on the spline. We won't need to do anything special here. We will just need to have a uniform distribution of 100 particles along the entire spline. You can change that if you wish. You can have it only along part of the spline, just the endpoints, if you invert these, whatever you really want there. But in here, let's go ahead and you don't need to worry about the lifetime. We will never be killing these particles, so we can just leave that there. We can set this to a nice red. And on our ribbon attributes, we can give this a ribbon width of 10. Now we can go to our particle update and we can set a ribbon as the spline. And we have 100 ribbon segments here. And then we can scale the ribbon width over time to give it that pulsating effect. And on the particle states, we will not kill particles when the lifetime has elapsed. And we can leave it as that. Just pop in a ribbon renderer to show this ribbon. We won't need to change the material or anything for this ribbon. It will just be simple and red. So on a ribbon width, let's go ahead and make this so we can have our ribbon pulse over its lifetime as well. And that way we can have the ribbon pulse over its lifetime, and also so it can only show when this is being pushed instead of when it's closed. If it's closed, we don't want to see the ribbon because then that will get confusing. So if we go and put in a waveform here, this way we can make a good compound wave here, and it will oscillate somewhat randomly. It's still pretty predictable in the sense that you can get the idea it's pulsing with purpose, but it's still random enough so it can feel a bit more natural. And so the amplitude scale, this will really depend on whether or not the ribbon is enabled. Now, if it is going to be animated, like I said, I will want that ribbon to be visible at all times and having its force being distributed at all times. So I want to make another Boolean float here and say if I am animating this, I will want it to constantly have a amplitude of 2. Otherwise, we can put in our sine wave we had from earlier with our 10 period and then 2 scale and 2 bias this time. And this way we can get a good amount of pulsating from this ribbon here. And then down here for this wave, our phase scale, we can leave that as 1. Our compound frequency, so that does something about 4, and then give it a bit of a decimal so it can be offset by some amount to make it a bit more natural. Same with frequency, we can set this to 2 and then a bit of a decimal after it. The amplitude minimum and maximum, we can leave that the same since our amplitude will be augmented by this up here. And then scale and bias, we're good to leave as is. So now if we save this and go look at this, we can see our ribbon. A bit harder to see here, but it is pulsing. You can see right there, it's pulsing back and forth, and it is acting very similarly to this ribbon over here. What we can do if it's not visible enough is we can just go in there and blast our red color a bit more, so we can set this to something like 10 instead, and it will make the ribbon much more glowy, we can see. But now the ribbon's much more visible. On the other system, I believe I set it to something closer to 100 though, so we can try and see what that looks like. At 100, save that and check it, and now we can see we have a clear red pulsing ribbon. It looks somewhat see-through, but at the same time, not really. We can see it pulses. You push these particles away, and then it kind of dies out, and the particles come back into what was pushing away, and it makes the tunnel again. But what I also would like is for these particles around the outer edge here to have a color similar to that of this spline on the inside, to kind of really sell the fact that this spline right here is affecting these particles as they're pushed. So what we can do is we can go back into here and we can set the particles color directly here. So if we go to color, we can go to the particles color, move this up to the top so this way this happens first. And so what we will want is when they are being pushed, we will want a color for something like a red or an orange, and then when it's not being pushed, we want it to be this default color right here. So we can go and get another lerp here, and we can lerp linear colors. Our start color, like I said, will be that kind of more orangey color. And then we can go over here and just copy our normal color. And then on here, we can use the oscillation that we have from our attractive force and create a similar value here for our lerp. So we can clamp it again. And we will have a minimax of 0 and 1. And again, we will have our distance between positions. So at this point, I will just go and duplicate this part right here. And we'll also be taking this chunk as well, because if it is animated, I will want it to have this brighter color all the time. We can just duplicate this entire section right here. So we can copy and we can paste it right in there. So this all right here will work just fine for that part right there. And then if this part is animated, I will want to set this something like 400. And then in this case, I will want this to also have a total scale of 400. So to do that, I start with an initial scale of 400. Since it's a sine wave, it will go positive and negative. So we'll need to add another bias of 200 to kick it up above the axis. And we will have 400 total between those two. And then once we have this node set, we also want to make sure we get rid of the scale color node so that doesn't affect anything, since we don't need the scale color over lifetime here. Now if we look at it, we have this orange color near the outline of the ribbon. It will collapse. Then we'll start pushing these particles back out again and give it this orange, red, pinkish tone when the tunnel is created. And what we can do now is first let me rename this to cloud clearing. But what I can do is if we go to the emitter, we can go and have it make the tunnel instead, and we'll see it collects these particles onto the outside, and then it collapses and forms this cloud again, and it opens back up and forms that. So the next step is animating the spline. This can be done through a variety of methods. The method I will be showing you here today is actually creating a child of the current Streamline blueprint, and we can call this Streamline Spline Emitter Cloud Clearing. And we can bring this into our folder here. And what we can do is if we open this up, we have our little spline right here. And then we will have this event graph. And what I will do in here is I will be creating a timeline that I will animate that spline over. So I can drag this out first here, and we will clear the spline points of the spline that we have in this blueprint here. We can drag that out, and then we will connect it over to there. And what I will do is create a for loop where I add all of the spline points I would like. So we can get for loop, and I'm going to add four points, so that'll be index 0 to 3 of the points. Now what we can do is make an add spline points, and this will automatically add it counting up the indexes, so I won't need to worry about that adding something at a random index. And we can just make a vector here, and it will just be at the origin of the blueprint here, in local space as well. And then we'll want it to update the spline when we do this. So what we'll want to do is pass this down to our parent begin play, and then we'll want to create a toggle for running this timeline. This way it can be switched off properly so it does not repetitively start the timeline, because what can happen is if you don't stop it once you start playing the timeline, when you feed it back into itself, it will start the timeline over and over, and you will either see no difference with the timeline or a lot of spline points and start to have weird behavior to them. So we can call this variable run timeline, and this will just be a Boolean right here. You don't need to access this externally, so we can just leave it private. And on our event tick, we can get rid of our event overlap here because we do not need this. But on our event tick, we can go and make sure our parent ticks first. Then we'll make a branch, and this will just say, has our timeline been run yet? And am I good to continue to run the timeline? And if we are, that means we will want to set run timeline to false, because that means now I'm going to go ahead and run the timeline again. And then we can go and make a timeline. So add timeline. We can call this spline animation. We'll want this switch here to play it from the start. Otherwise, we will want this tick to just play another tick of the timeline. And we can move this over and duplicate this, because we will want this to make sure it sets run timeline to false as well, because this part will initially play this from the start as well. And then once it's finished, we will want to run the timeline again, so we will set this back to true. So now what we'll want to do is we will want to add set location at spline point nodes for all of the spline. We'll update them. This first index will be 0. We'll have index 1, and then 2 and 3. Once these are all added in, we can hook them all up. And we can then wire this spline between all of them. So I'm going to be using reroute nodes here. And now what we'll want to do is give each of these spline points animated locations. You could also do this through a for loop, where you just say, for each point index, I want to give it this specific location to go to. And you could do this by putting all of the vector tracks that you create into an array and then just looping through that array and basically mapping it to all of these points. However, this is a small enough set of points where I'm just going to do it by hand to really show you the process here. So if I open up the spline animation node right here, we can go and add a track, and we can add a vector track. We will call this point 1, and then I will add 3 more of these tracks. Okay, now we have all of the tracks. What we can do is we can hook these up here. So now all of these points have their respective tracks attached. So I can compile this, and if we go over to our tracks, we can animate these points however we want. We just need to keep in mind that it is going to be a line, so we will need to animate these in the order we will want them to be connected as well. So when we think about where our origin is here, our origin is all the way at the end right over here. So we will want to animate all of our points spreading out this way in the negative x direction. And so we will want to ensure that all of our points head out that way. What we can do is we can first just hide the y and z, and we can only worry about the x. This is done in increments of seconds here. So if I zoom out, we can add a key to just this curve right here. We'll also want to add a key at 0 to hold it right there and its beginning location. And then for this key, we can do, let's just say at a time of 5 seconds, we will want to move it out by 300 centimeters. 300 centimeters. Click enter, and then it gets blasted way up there. We can close that. And we can zoom to fit the vertical there. And so what we'll want to do is we'll want to copy this motion over for all points if we want to create a continuous spline. We can open up all of these. We can hide the Y and Z on all of them. And this really gets to be a somewhat repetitive process, but it's pretty simple. And I will just speed this up right here so you can see me just animating out all of these curves, and then you can see the final product. Okay, so I finished drawing out all the animation there in keyframes. We will want this so we can sample the spline from it, but what we will want to do, bring out this Streamline system and sample this spline right here. And now we have the spline again. Bring it back down over to here, roughly about there. Hide this, and we can give our child Streamline emitter here the cloud clearing Streamline system again. Bring it down to the emitter, and we will turn on animation and tunnel. So now it will start from this end and draw itself out. We can get rid of this cloud clearing. In fact, we will not need it since we have our child emitter here. So we can play. You can see it's starting here, and it is actually animating. It's just hard to see it working here because of all of this. So what we can do, we can go back into our blueprint here, and instead of changing those keys, we can just change the output of those keys right here by just doing some simple multiplication to make their effect more obvious. So we can just multiply all of these vectors by some negative big number to make them more obvious. So let's just multiply them by -5 each. This may be too effective, but this is one way to quickly change these keys without actually worrying about having to redo all of your keying, because that will be annoying. So instead, you can just use some math on the other ends and change it much faster. So for example, mine were going the incorrect direction, so I had my spline drawing out this way. And what I instead do is I want it to draw out this way, so I multiply it by a negative number, and then it will draw out this way. If I press play, I can see it moving along over here. And it just moves along this path. So this is one method. So instead of animating an entire spline, I just animated a part of the spline. And one other thing worth noting is that this spline reset to its default instead of the one you created it as. So if you want a more transient spline, you can sample from other splines. For example, if I was to go sample from the cloud clearing over here, sample that spline out, we now have it in this direction, of course. So I would take these spline points, I would select them, and just simply move these points over in this direction. And so that is something you will want to consider, is make sure that this thing's saved if you started without it being saved. There's no guarantee if you clear that spline in the animation, it will come back. So you need to make sure that you save it as is, otherwise that animation will clear it and it can't reset properly. As you can see, my animation, I animated basically the whole blob of spline points moving along. This is one option for what you can do. There are many possibilities, really. You can animate it however you would like. For example, I could go back here and just change these keys real quick, completely move them around. And get some wildly different points. So now if I am to run it, I now draw out this spline. In this case, it's going way over there. But super simple. And you can animate however you want. This is one option. You can also animate splines through other different sequencing methods. You can have an in-game character even draw out a spline behind them as well. That's something interesting you could do. You can use this to make some very interesting trail methods and have particle effects related specifically to those trails. And this way you can have splines do those trails instead of just the particle system itself. So you can have a more interactable trail in other senses instead of just a particle effect. Pretty simple tutorial. You just learned how to make these two emitters in the Niagara system and how to child the Streamline blueprints and turn it into a more customized emitter for you. So this way you can have an animated emitter where its range will change at runtime. Again, you can do this through other methods as well. You can create a sequencer. You can do all kinds of things with this. So that wraps up particle clearing with Streamline. Thank you for watching. If you found this video helpful or informative, please leave a like so you can help other people find it. And don't forget to subscribe to the Galactic Games YouTube channel and ring the bell so you can get any notifications about updates and information from Galactic Games. And also check out our Discord community so you can engage with other people using products such as Streamline. I hope you learned something in this tutorial and that you can use this to make amazing Streamline Niagara systems.